In this video, I will be discussing about random variables and probability functions. Specifically, I will be talking here discrete random variables and discrete probability distributions. So first, let us define what is a random experiment. A random experiment is any process or activity that generates a set of data wherein each outcome is influenced by chance. And statistical experiments are conducted in order to produce results which we call events. And these events have probabilities of occurring, and these probabilities can be obtained by the use of counting principles, which we've learned in the previous videos. However, obtaining the probabilities of each and every event could be a cumbersome process. So therefore, we may find some ways in order to ease the computation. Fortunately, these probabilities of events in some statistical experiment can be kept in a formula. When one deals with formula, events must be translated numerically, and this translation process paved the way in the development of the concept of a random variable. So, what is a random variable? A random variable is a function whose value is a real number determined by each element in a sample space. And mathematically, a random variable x is a function from the sample space S into the set of real numbers R, such that for each interval I in the set of real numbers, the set of all S is an event in the sample space. Now, the sample space of a random variable is the set of all x in the set of real numbers, such that this x is the specific value of the random variable x of every event in the sample space. Now, in this video, I will be discussing about discrete sample spaces. A discrete sample space is a sample space which contains a finite number of possibilities or an unending sequence with as many elements as there are whole numbers. And discrete random variable is a random variable which can assume at most a finite or a countably infinite number of possible outcomes. So, a probability distribution or a probability mass function is the set of ordered pairs x and f of x of the discrete random variable x if for each possible outcome x, the following are satisfied. Number 1, f of x is equal or greater than 0. In other words, f of x can never be negative. Number 2, summation of all f of x for all x must be equal to 1. Number 3, that the probability of this random variable x, which has a specific value of the small x, is equal to the f of the small x. Now, to illustrate this probability distribution or a probability mass function, we'll have our example 1 here. And suppose we will perform a statistical experiment which is tossing the 3 coins simultaneously, and let x be a random variable whose value represents the number of heads as outcomes. So, if you list down all possible outcomes of this experiment of tossing 3 coins simultaneously, we can have the result of all 3 heads for the 3 coins, or 2 heads for the 2 coins but a tail in 1 coin. Or you can have a head in the first coin, a tail in the second coin, and a head in the third coin. Or we can have a head in the first coin and tails for the other 2. Or we can have a tail in the first coin and heads of the other 2 coins. Or a tail in the first coin, a head in the second coin, and a tail in the third coin. Or the first 2 coins resulting two tails and a head in the third coin, or all of them are tails. So since our random variable x represents the number of heads as outcomes, we can find our random variable x for the first result here, which is having all heads for all the coins. So our random variable there is having a value of 3. But in the second outcome, we have the random variable which is equal to 2 because we have 2 heads there. And in the third outcome, we still have 2 since we have 2 heads in the outcomes. And the next outcome, we have 1 as the value of our random variable because we have only 1 head in this outcome. And the next is 2 there, 1 for the next, and also 1 for this outcome. And lastly, we have 0 here since the outcome has no head as a result. So as you notice that the least value of the random variable is 0 and the highest value there is 3. Thus, tabulating this one in a table, we can have all the possible values of our random variable from 0, 1, 2, and 3. And we can compute its corresponding probability based from all possible outcomes. And you notice that there are 8 possible outcomes when you toss 3 coins simultaneously. And out of the 8 possible outcomes, there is only one possibility that there is no head at all. So therefore, the probability is 1/8. But when the random variable x is having a value of 1, it can occur in 3 ways because 1 indicates there as having exactly 1 head as a result. So the head can occur in the first coin, or in the second coin, or in the third coin. So therefore, the probability is 3 out of 8 chances. But the value of 2 for the random variable x will have a probability also of 3/8 because there are 3 possible outcomes out of 8 outcomes there. But there is only 1 out of 8 outcomes that has all heads in the result. So therefore, we say that this table containing 2 columns, or in the first column are the values of the random variable, and the second column are its corresponding probabilities, then this table represents a probability distribution. So what is a probability distribution? It is a set of all possible values of the random variable and its corresponding probabilities. Actually, the first table there is not our answer in this example number 1, but we do that first table so as to facilitate the construction of our final table, which is the probability distribution of the statistical experiment of tossing 3 coins simultaneously. However, we can represent also a probability distribution by a formula, and this formula is what we call a probability mass function for a discrete random variable. So how can you represent this probability distribution through a function? The function is f of x, where our x can have values from 0, 1, 2, and 3. So these values of x are what we call the values of our random variable x. And our function can be constructed as the combination of 3 taken x at a time, where the denominator is a product of the 3 2's there. And why 3 2's? Because you have 3 coins that are independent of each other, and each coin can result in 2 ways, as head or tail. So the first coin could land head or tail, the second coin could land also as head or tail, and so with the third coin. But in the numerator, we are counting all the possible outcomes by using the combination formula as the combination of 3 taken x at a time, because the combination of 3 taken 0, wherein that is the least value of our random variable, the answer is 1. So therefore, our probability when the random variable is 0 is 1/8. And you can check that when there is no head, the probability is 1/8. But when our random variable is having a value of 1, then we can compute its probability by this formula as 3 taken 1, which is 3. So the probability is 3/8. That's why when your random variable is 1, the probability is 3/8. But when your random variable is having a value of 2, we can use this formula as the combination of 3 taken 2 at a time. And 3 taken 2 at a time is 3. And you can check that when the random variable is having a value of 2, the probability is 3/8. But when your random variable is having a value of 3, using this formula, 3 taken 3, the answer is 1. So the probability when your random variable is having a value of 3, the probability is 1/8. And you can check it here from the table that when your random variable is 3, the probability is 1/8. Hence, this formula is a representation of a probability distribution because it contains the values of the random variable here and its corresponding probabilities, which is represented by f of x. Now, let's proceed to our second example here. Consider a statistical experiment of drawing 2 balls in succession without replacement from an urn containing 5 red balls and 4 blue balls. And let y be a random variable whose values represent the number of red balls as outcomes. So, listing all possible outcomes, we have all the 2 balls drawn in succession are all red. Or you can have a red ball during the first draw and a blue ball during the second draw. Or you can have blue first and then red ball in the second draw. Or maybe both of them are blue balls. So the values of our random variable here in the first outcome is 2, since our random variable y represents the number of red balls in the outcome. And in the second outcome, we have only 1 because we have exactly 1 red ball here. And so with the third outcome, we still have a value of 1 in our random variable y because we only have a red ball during the second draw. And in our last possible outcome, we have 0 as the value of our random variable y since we don't have any red ball here. Now, constructing our probability distribution, our random variable can assume values from 0, 1, and 2. And 0 is having a probability of 12/72 since during the first draw, we only have a blue ball. And obtaining a blue ball in this urn of 5 red balls and 4 blue balls, the probability is 4/9. And this will be multiplied by the second probability for the drawing of the second ball, which is 3/8, since we only have a remaining 3 blue balls chosen from the remaining 8 balls from the urn. So multiplying this one, we have 12/72. But this value of the random variable y, which is 1, can have a probability that is obtained by drawing exactly 1 red ball. And drawing a red ball from this urn is 5/9. And this will be multiplied by the probability of obtaining a blue ball from this urn. And there are 4 blue balls from this urn out of the 8 remaining balls from the urn since we don't replace the ball after the first draw. But remember, obtaining exactly one red ball can occur in two ways. So that is why we multiply it by 2. And this can be obtained by drawing a red ball in the first draw or drawing exactly one red ball during the second draw. So multiplying these numbers, we have the probability of 40 over 72. So this is the probability of obtaining exactly one red ball. But when the random variable is having a value of 2, which represents 2 red balls when you draw 2 balls in succession from this urn, can be obtained by the probability of drawing a red ball during the first draw, which is 5 over 9, and this is multiplied by the probability of drawing another red ball during the second draw, which is 4 over 8, and multiplying these numbers, we have 20 over 72. So therefore, this table represents a probability distribution of the statistical experiment of drawing 2 balls in succession without replacement from an urn containing 5 red balls and 4 blue balls. However, we can represent this probability distribution through a formula, and the formula will be f of y, since our random variable is y, where y can have values 0, 1, and 2. And the formula is this one, 2 times the combination of 5 taken y times the combination of 4 taken 2 minus y at a time. And why is it that we have 5 taken y? Because there are 5 red balls in the urn. And why is it that we have a combination of 5 taken y at a time? Because we have 5 red balls in the urn. And y represents our random variable here. But this is multiplied by the combination of 4 taken 2 minus y at a time, since we have 4 blue balls in the urn. And you choose here 2 minus y balls, which depends of how many balls you choose from the red balls, and this will be subtracted to 2 since we need to draw only 2 balls here, but the denominator is 9 times 8 since you will be drawing in succession 2 balls from this urn. So during the first draw, you can choose any of the 9 balls in the urn times 8 remaining balls during the second draw. So this formula represents a probability distribution since it contains 2 parts here, the values of the random variable and its corresponding probabilities, which is represented by the formula f of y, which we call here in the discrete random variable as the probability mass function, or in short we call it PMF. Now let's proceed to our example number 3. Consider a statistical experiment of choosing a pair of dice, and let W be a random variable whose values represents the sum of the points obtained in choosing a pair of dice. Now, drawing a grid here for accounting all possible results, we can have 2 as an outcome here, since the first die could land 1 and also the second die, so the sum is 2. Or you can have 3 here, since the first die could land 1 and the second die as 2. So therefore, 1 plus 2 equals 3. Or you can have 4 as the sum of 1 and 3. Or you can have 5 as the sum of 1 and 4. Or 6 as 1 and 5. Or 7 as the sum of 1 and 6. And so on and so forth, tabulating all possible sums here. We have 36 all in all, because the first die could land in 6 ways from 1 to 6, and the second die also could result in 6 ways from 1 to 6, since the 2 dice are independent of each other. Now, drawing our table representing the probability distribution, we can have our values of our random variable W from 2 to 12, since you observe in the grid I have drawn at the left side of this presentation, wherein 2 is the smallest sum and 12 is the highest sum here. And the probability of obtaining a sum of 2 is 1 out of 36. And the probability of obtaining a sum of 3 can occur in 2 out of 36 from the sum of 1 plus 2 and 2 plus 1. And also the probability of obtaining a sum of 4 is 3 over 36. And the sum of 5 is 4 over 36. And the sum of 6 is 5 over 36. And so on and so forth from this grid at the left. So therefore, this is our representation of a probability distribution for this experiment of choosing a pair of dice. And again, you notice that a probability distribution contains two parts. The values of the random variable, which you can see in the first column, and its corresponding probabilities, which you can see in the second column here. Now, we have there in the second column as the probability of the big W, which is our random variable, which is equal to the small w, which is the specific value of the random variable big W. However, this probability distribution can be represented by a probability function, which is f of W, where W is our random variable having values from 2 to 12. And you must be clever enough to create a function that describes the probability for each value of the random variable. And the formula is 6 minus the absolute value of W minus 7 divided by 6 times 6. And obviously, the denominator is just the fundamental principle of counting, since the first die could land in 6 ways, multiplied by 6 ways that the second die could result. And the numerator takes a little creativity of constructing this mathematical model to represent these probabilities of the sum of the points obtained in choosing a pair of dice. But in summary, this represents also the probability distribution for this statistical experiment of choosing a pair of dice, because it consists of two parts: the values of the random variable and its corresponding probabilities, which is represented by the probability function f of W, which we call here in the discrete case as the probability mass function, or in short, we call it as the PMF, as the shortcut for the probability mass function. Now, proceeding to our fourth example, consider a statistical experiment of choosing a balanced coin 4 times, and let Z be a random variable whose values represents the total number of heads obtained after a coin is tossed 4 times. Now, accounting all possible outcomes, let us list down the sample space. You can have all the 4 results as heads, or you can have the first 3 tosses as heads, or you can have heads in the first tosses and a tail during the third toss and a head in the fourth toss, or you can have there head, head, tail, tail, or head, tail, head, head, or head, tail, head, tail, or head, tail, tail, head, or head, tail, 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 and so on and so forth. And maybe you will ask a question, how will you list down all possible outcomes? And you can do that by drawing a tree diagram. So our first outcome is having a value of 4 in our random variable, because we have here 4 heads as an outcome. And the next one is 3, since we have only 3 heads out of the 4 tosses of the coin. Then 3, then 2, then 3, 2, 2, 1, 3, 2, 2, 1, 2, 1, 1, and 0. Since our random variable z represents the number of heads, so you just count how many heads in the outcome. So constructing our probability distribution for this statistical experiment, we have our random variable z to assume values from 0 to 4. Because as you noticed, in the listing of the sample space, we have 0 as the smallest possible value of our random variable and 4 as the highest value, since we are tossing the coin 4 times here. And 0 could occur in 1 out of 16 possible outcomes. But 1 is occurring 4 out of 16 possible outcomes if you count how many ones here. And 2 occurs in 6 possible ways. 1, 2, 3, 4, 5, and 6 here. While 3 occurs 4 times. 1, 2, 3, 4. While 4 occurs only once there. Thus, this table represents a probability distribution. But then again, a probability distribution can be represented by a formula, and the formula must consist of 2 parts. And the first part is the probability mass function, PMF, which is f of z. And this is represented as the combination of 4 taken z at a time, since we toss the coin 4 times here, where z is our random variable assuming values from 0 to 4. And in the denominator, we have 2 times 2 times 2 times 2, because the first coin could land in 2 ways, independent of the result of the second coin, which is also 2 ways, and the same with the third coin and also the fourth coin. Hence, this formula represents a probability distribution of the statistical experiment of tossing a balanced coin 4 times, since we have 2 parts here, the values of the random variable z, assuming values from 0 to 4, and its corresponding probability, which is represented by the probability mass function f of z here. Now, going back to our example number 1 of tossing 3 coins simultaneously, and our random variable x, which represents the number of heads as outcomes, we have this table as the representation of our probability distribution. And also you can represent this one using a formula of f of x, where x is a random variable from 0 to 3. And you can see here that a probability distribution can be represented by a table or a formula. But we can also represent this probability distribution for this particular statistical experiment using a graph. Now, since this is a discrete random variable, because we have finite values of our random variable from 0 to 3, we construct our first bar for the random variable 0, having a probability of 1/8, and also our random variable 1 having a probability of 3/8, and also random variable 2 with 3/8 as its probability. And lastly, the random variable 3 having a probability of 1/8. And you can see that this graph also represents a probability distribution, because you see here 2 parts, the values of the random variable, which you can see in the x-axis, and its corresponding probabilities in the y-axis. Then therefore, a probability distribution of a statistical experiment can be represented in three ways here. You can represent through table, or you can represent using a formula, or represent using a graphical representation. Now let's proceed to our example number 2 of drawing two balls in succession without replacement from an urn containing 5 red balls and 4 blue balls, where y is the random variable whose values represents the number of red balls as outcomes. And we know that we can represent that one using a table that has two parts, where the first part are the values of the random variable and the second column has its corresponding probabilities. Or you can represent that one using a formula. But then again, you can represent using graphical representation, wherein the x-axis are the values of our random variable 0, 1, and 2. And for our random variable 0, we will draw a bar whose height is 12 over 72, since the probability is 12 over 72. But for the random variable 1, the bar must have a height of 40 over 72, while the random variable 2 is having a height of 20 over 72, since its probability is 20 over 72. So you can see there three representations for this statistical experiment. You can represent the probability distribution through table, through a formula, or a bar graph here, where the values in the x-axis are the values of the random variable, and the values in the y-axis are its corresponding probabilities. Now, recalling our example number 3, with a statistical experiment of choosing a pair of dice, where W is the random variable whose values represents the sum of the points obtained in choosing a pair of dice, we have this table as a representation of our probability distribution, where the random variable W can have values from 2 to 12 and its corresponding probabilities in the second column here. But this can be represented in another way, which is through a formula there, where f of W is our probability mass function and W is our random variable. But then again, this probability distribution can be represented by a third way, and this third way is through graphical representation, wherein the values in the x-axis are the values of our random variable, and the values in the y-axis are the values of our probability. So for the random variable 2, we have a probability of 1 over 36. For 3, the probability of 2 over 36. For the random variable 4, 3 over 36, and so on and so forth here. Hence, you can see that there are three ways of representing a probability distribution: using a table, or using a formula, or using a graphical representation. Now, recalling our fourth example in this lecture, we have the statistical experiment of choosing a balanced coin 4 times, where Z is a random variable whose values represents the total number of heads obtained after a coin is tossed 4 times. Now, our probability distribution can be represented through a table, where in the first column are the values of our random variable Z from 0 to 4. And also the second column are its corresponding probabilities. However, we can represent this table using a formula. And our formula for our probability mass function is f of z. And this f of z is the combination of 4 taken z at a time. all over the product of 4 2's, where z can have values from 0 to 4. And this representation is a functional representation of the probability distribution. But then again, we can represent this probability distribution using a graphical representation, wherein the values in the x-axis represents the values of the random variable and the values in the y-axis as its corresponding probabilities. So the first random variable 0, we have a probability of 1 over 16. And for the random variable 1, having a probability of 4 over 16. Random variable 2 with probability 6 over 16. Random variable 3 with probability 4 over 16. And lastly, for the random variable 4, having a probability of 1 over 16. Then you can see here that there are 3 ways of representing a probability distribution, using a tabular representation for this probability distribution, or you can have a functional representation for this probability distribution, or you can have a graphical representation for this statistical experiment of tossing a balanced coin 4 times. Now, there are several problems in which it is of interest to know the probability that the value of a random variable is less than or equal to some real number x. And suppose we write this probability that x takes on a value less than or equal to x as the big F of x, which is equal to the probability of our random variable whose value is less than or equal to the small x. For every real number, small x, we define the big F of x to be the cumulative distribution of the random variable big X. And this notion paves the definition number 3. The cumulative distribution big F of x of a discrete random variable x with probability small f of x is given by this big F of x, which is equal to the probability of our random variable x whose value is less than or equal to the small x here, which is equal to the summation of all probability values of t, where t is less than or equal to small x, for x is a real number, where f of t is the value of the probability distribution of x at t. And this big F is called the distribution function, or the cumulative distribution of the random variable x. In short, the big F of x is the representation of the cumulative distribution function of our probability mass function small f of x. And to illustrate this concept, let's have an example here. 2 sacks are drawn at random and removed in succession from a drawer without replacement after the first draw. The drawer contains 5 brown sacks and 3 green sacks. And let random variable x be the number of brown sacks. Determine its cumulative distribution big F of x. Now first, let us represent the probability distribution for this experiment of drawing 2 sacks in succession from this drawer, where x is the number of brown sacks. So you can have no brown, or you can have exactly 1 brown, or all of the 2 sacks are brown, and the probability of obtaining no brown sacks is to draw green sacks here. And since there are 3 green sacks out of the 8 sacks in the drawer, we can have 3 over 8, and this will be multiplied by the probability of the second draw, which is 2 out of 7 here, because we have 2 green sacks as the remaining green sacks in the drawer after the first draw. So multiplying these numbers, we have 6 over 56. And having a random variable 1 is to draw exactly one brown socks. And drawing exactly one brown socks is to draw 5 out of 8 here. And this will be multiplied by 3 over 7 since the second draw is to draw a pair of green socks. But obtaining exactly one brown socks can be done in two ways. So that is why we need to multiply this one by 2. So multiplying this one, we can have 30 over 56. But drawing 2 brown socks from this drawer is obtained by multiplying 5 out of 8 by 4 over 7, since we need to obtain a brown socks during the second draw. So multiplying this number, we have 20 over 56. So this is the probability distribution for this experiment here. So our cumulative distribution function of big F of 0 is equal to the small f of 0. Now, take note that big F is the sum of all probabilities from 0 and all values below 0. But because there is no value below 0 in the random variable, this is just equal to the small f of 0, having a value of 6 over 56, which can be reduced as 3 over 28. But for our big F of 1, which represents for our cumulative distribution function of 1, this is equal to the small f of 0 plus the small f of 1. Since big F is the sum of all probabilities of the random variable from 1 and below. So that is why we have here small f of 1 plus small f of 0. And we know that the probability of the random variable 0 is 6 over 56. And the probability value of the random variable 1 is 30 over 56. Now adding these two probabilities, we have 36 over 56, which can be reduced as 9 over 14. So 9 over 14 is our big F of 1. So this is the sum of all probabilities of the random variable from 1 and below. But for the big F of 2, this is the sum of all the probabilities for the random variable starting from 2 up to the least value of the random variable, which is 0. So this is equal to the small f of 2 plus the small f of 1 plus the small f of 0. But we know that the small f of 0 is 6 over 56 and the small f of 1 is 30 over 56, while the small f of 2 is 20 over 56. Adding these three fractions, we have 56 over 56, which is equal to 1 here. So constructing our big F function or the cumulative distribution function, we have a probability of 0 for all random variables below 0. And since there is no below 0 in our random variable, therefore our probability is 0. But when your random variable is from 0 to a number below 1, so this is 0 only in the integer, we have the probability of 3 out of 28. But for our random variable from 1 up to a number below 2, we have the probability of 9 over 14 as we solved here in our solution. And for the random variable from 2 and above, we have the probability of 1 here, which we solved it here. Hence, this big F of x is the cumulative distribution function for this statistical experiment. Now, let's proceed to our fourth definition here. The values of the big F of x of the distribution function of a discrete random variable x satisfy the following conditions: that the cumulative distribution value of negative infinity is 0, since there is none to the left of negative infinity. But the cumulative distribution function of infinity is 1, because this is starting from the left up to the positive infinity. So it's obvious that the cumulative distribution value of positive infinity is 1. Number 2, if you have a random variable a which is less than the random variable b, the cumulative distribution value of a must not exceed the cumulative distribution value of b for any real numbers a and b, which means that the cumulative distribution function is increasing. It is a monotonic function. Now, recalling our previous example of choosing a balanced coin 4 times, where z is a random variable whose values represents the total number of heads obtained after a coin is tossed 4 times, determine the cumulative distribution big F of z for this random variable z. Now, we have obtained this one already, the tabular representation of the probability distribution for this statistical experiment. But solving for the big F of 0, this is equal to the small f of 0, which is equal to 1 over 16. And the big F of 1 is equal to the small f of 1 plus the small f of 0, because big F is the sum of all probabilities starting from 1 down below. And the probability of the small f of 0 is 1 over 16, while the value of f of 1 is 4 over 16. Thus, the total is 5 over 16. And solving for the big F of 2, it's the probability of the random variable 2 plus the probability of the random variable 1 and the probability of random variable 0. So adding these 3 individual probabilities, we have 11 over 16. But the big F of 3, it's the sum of the individual probabilities when the random variable is 3 added to the random variable is 2 added to the probability of the random variable of 1 plus the probability of the random variable 0. So adding these 4 individual probabilities, we obtain 15 over 16. And lastly, for the big F of 4, and the big F of 4 is the sum of all individual probabilities from the random variable of 4, then 3, then 2, then 1, up to 0. And we have the sum of 16 over 16, which is equal to 1. So constructing our cumulative distribution function of big F of z, we have the probability of 0 when your z is below 0. But since there is no value below 0 here, so that is why the probability is 0. But when your z is from 0 to a number below 1, the probability is 1 over 16, as we have seen in our big F of 0. But when your z is 1, the big F of 1 is 5 over 16. And the big F of 2, we know that's 11 over 16. And the big F of 3 is 15 over 16. While the big F of 4 is 16 over 16, which is equal to 1. Hence, this big F of z is the representation of the cumulative distribution function. Now, let's proceed to our fifth definition here. If the range of the random variable x consists of the values of x sub 1 being less than x sub 2, less than x sub 3, and so on, which is less than x sub n, then the probability of your random variable whose value is x sub 1 is equal to the cumulative distribution function of big F of x sub 1. and the individual probability of small f of x sub I is equal to the big F of x sub I minus the big F of x sub I minus 1 for I from 2 to n. In other words, this definition is saying that we can compute the individual probability given a cumulative distribution function of a particular statistical experiment. In this case, we can reverse the process illustrated in the two preceding examples. That is, we can obtain values of the probability distribution of a random variable from its given cumulative distribution function. So, given a cumulative distribution function of x, which is given by this big F of x, we can compute these following probabilities. What is the probability when your random variable is equal to 5? And solving for this probability of the random variable which is equal to 5, this is equal to the big F of 5 minus the big F of 4, because you know the big F of 5 is the sum of all probabilities from 5 and below. But this big F of 4 represents the sum of all probabilities of the random variable from 4 and below. So from 5 and below minus from 4 and below, the remaining is the random variable of 5. So solving for the big F of 5 from the cumulative distribution function, we have 10 over 36, which is found here since our random variable is 5. And this is subtracted by the big F of 4. And the big F of 4 is here, where the probability is 6 over 36. Now, subtracting these two fractions, we have the difference of 4 over 36. Then therefore, the probability for the random variable whose value is 5 is equal to 4 over 36 here. And solving for the probability value for the random variable of 6, we have the big F of 6 minus the big F of 5, since the big F of 6 is the sum of all probabilities from 6 and below, and the big F of 5 represents the sum of all probabilities from 5 and below. So from 6 and below minus from 5 and below, the remaining random variable is only 6. So therefore, the probability of the random variable whose value is 6 is equal to 15 over 36 minus 10 over 36. And how did I get the value of 15 over 36? We just locate it here in the cumulative distribution function. When the random variable is 6, the cumulative distribution function value is 15 over 36. But when your random variable is 5, its cumulative distribution value is 10 over 36, which is found here. So subtracting these two fractions, we have 5 over 36. And this is the probability value of the random variable whose value is 6. But for the probability of the random variable whose value is 8, this is equal to the big F of 8 minus the big F of 7. And the big F of 8 is 26 over 36. And we just locate it here from our cumulative distribution function. When your random variable is 8, the cumulative distribution function value is 26 over 36 minus the big F of 7, which is 21 over 36, since our random variable is 7. So subtracting these two fractions, we have 5 over 36. Hence, the probability of the random variable whose value is 8 is equal to 5 over 36. And also for the probability of the random variable of 9, this is equal to the big F of 9 minus the big F of 8. And the big F of 9 is here, which is equal to 30 over 36, minus the big F of 8, which is 26 over 36. So subtracting these two fractions, we have 4 over 36. And this is the probability value for the random variable whose value is 9. And lastly, solving for the probability of the random variable 11. This is equal to the big F of 11 minus the big F of 10. And big F of 11, you can see in the cumulative distribution function, which is equal to 35 over 36 as its probability value. And this will be subtracted by 33 over 36 because when our random variable is 10, the cumulative distribution function value is 33 over 36. So subtracting these two fractions, we have 2 over 36. Hence, this is the probability value of the random variable whose value is 11. So, in this example, we illustrate how to compute individual probabilities given the cumulative distribution function of our random variable. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.